So let's assume this is a rock mass, and we want to go in there to create a space. So this is the space we have created. As soon as we create this space now has the burden of carrying all the stresses from the top of the ground surface down to where you have created that space. So it's just like you looking directly at your laptop, perpendicular, okay? And you've created, the laptop screen is the space you have created. So the whole of the top of the lid of the laptop up there are the materials that this laptop lid is supposed to bear. So again, assuming you have a story building where you've created a whole floor, the whole of that floor has that burden of carrying the other floors on top of it. So the other floors on top of it too, the skies or the surface where your roof is what we have denoted as Z, which is the depth of your excavation. So you are mining at 20, let's say 200 meters in the ground. So from the roof of your excavated space to the surface is what we denote as Z. So if we know the density of that material the excavated space or the roof is going to carry, then the stresses at the point Z, which is Z, is the hydrostatic pressure. And ZZ here is talking about we are trying to do the computation in the 3D, okay, where you have your X, Y, and your Z, okay? We are looking at it in this direction. So your stresses in the Z direction. So stress in the Z direction is going to be rho G Z. So you have the rho being the density of the material. Then you have the G being the force of gravity that is acting on that hanging material, which is this material here. The force of gravity. So you need to know the density of the material here and the force of gravity, which is a constant we know, and then multiplied by the distance, the depth at which you are considering that material. These three components together will give you the pressure that will be exerted on the material. So for example, if this space you created here were to be a pillar, this is how much pressure you are exerting on that particular pillar. And so your rho G, as we've seen earlier, is denoted as your unit weight. So if you want to compute your unit weight, take notes. The unit weight is the density of the material times acceleration due to gravity gives you this symbol, which we call unit weight of a given material, which is the rock in this case. So then we have learned earlier again that if I exert any stress on a body, it has a corresponding deformation on the axis of it. So if I put pressure on a device from here, it will have its corresponding effect on this axially. And if I exert a force axially, it will have a corresponding effect that will show along it, which is radially, okay? And so with that one, then it means if I am calculating the vertical stresses, then I should also remember that there will be a horizontal stress that will be coming or acting on the pillar as I consider the vertical stress. And that too, if I want to consider the horizontal stress, remember your Poisson ratio. That tells us how much deformation in terms of strain we should expect when we bring about that kind of deformation. And so we have this finally, and then you have this force here, the pressure you have computed as the vertical stress, you multiply it by your Poisson component, which is the horizontal deformation, to get your PXX or PYY. So let's move on to, so mine pillar design. So in the ideal system, the dimension of room and pillars are expected to be the same. That is what we always want. That I am mining and I want to bring about pillars. For ease of computation, if I choose that I want to go by square pillars, then all the pillars must be square, 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 square. And that will help me to do easy calculations and come up with my excavation ratio and all that I need to do regarding the analysis. So, and when it's like that, we call those type of pillars regular pillars. Okay, regular and same dimensions. So mine pillar design consideration: 1, find the strength of the pillar material, the material that is going to bear this stress, which you are using to design your pillars. You need to find the strength of it. If you know the strength, that is when you'll be able to tell whether it can bear the pressure or the stresses that are going to act on it. Then determine the load the pillar will carry. So find the strength. So just like you take a child to the farm and you harvest a sack full of cassava, you first have to tell whether that child can carry that bag of cassava to the house. Else you harvest and have to add that to your own load. So you have to determine the load it is going to carry. But then before you can tell, you need to know the strength. Then design the pillar sizes using what we call factor of safety. So you need to know the factor of safety, which we call, at that point, you'll be able to tell the limiting equilibrium. So when you define your factor of safety, you can then tell that, okay, with this factor of safety I have, if I leave my pillars in this state, they are going to be stable or they need improvement. And then this factor of safety of a pillar is calculated by dividing the strength of the pillar by the stress you are going to impose, where the stress here is referring to the load it is going to carry. And then this strength here is what you have computed in the lab or done your tests, your various tests you have done, which rock test you have done in the lab is what is going to tell you the strength of the pillars. So there are a number of analysis people use, but the most common one that is being adopted and which we are going to use for this analysis, this study, is what we call the tributary area loading concept. It is simple, and this is what it says. It states that when I have a given pillar and there is material sitting on it, the pillar only takes a section. When I'm considering it to the left, it takes half of the load, the pressure that is exerted on it, it takes half of it to the left, half of it to its right, half of it to its front, and half of it to its back. So assuming I am considering this man at the center here, and all these things are square pillars. So if this is a square pillar, this particular pillar, and this, assuming this is also another pillar, this is the plan view, okay? you are looking, it's just like these things I have drawn here. It's just like you sitting on top of a roof and you can see through. They've cut the building and they've hanged you up there, and you are able to tell where each pillar is standing or erected. Okay, so that is the picture we are painting with this image. And then if I want to check how much load each pillar can carry, because there's a pillar to this pillar's left right hand side, and there's another pillar, and since we are using square pillars, it means that the space here and the space here is the same. This is square, that is square, square, square. So what tributary area principle is saying is that this pillar will take up to the middle, the forces up to the middle. So assuming the load between them is 1. These two pillars, one is not greedy, more greedy than the other. So they will share the load equally. So this man here will pick half of the load. When it gets to its left side, it will pick another half of the load there from this other pillar on top of it. Pick half of it and then pick half of it here. So this empty space you see here, which I have denoted in red, this empty space you see here, okay? This empty space you see here is the room, the space you have created where you are mining. And then the black boxes are the pillars themselves. So the pillar has a dimension. We said it is a square pillar. So you have W represents the width, okay? So WP is width of pillar. WO, which is the gap existing between these two guys, is width of all. This same space there in some books, they call it gallery. So you will see in some books, instead of writing WO, they will put WG. Okay, so that is the space. And then to this side, we also call it the width of all or the gallery. Again, you have the same thing up here. So this, assuming you were to mine, you were going to have something like this. You are going to mine the whole of this, but the blue section is the amount of force or stress that pillar is going to carry. So each pillar is going to have that kind of distribution around it to tell us how much load it is able to bear.